and welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. I know that you were pretty excited about response surfaces after the last two lectures. Well, we got one more in store for you, and it's how to use them in practice. So the response surface is pretty cool. We've discovered that so far. But we also have to figure out how to use it in practice, because you don't always just fit a response surface model to your data. That truck needs its muffler fixed. You don't always fit a response surface to your data. What you have to do is consider fitting part of a response surface and then fitting the second half if it's worth it. We're going to look into that, and we're also going to look into how to actually analyze response surface data in R using the RSM package, which is a pretty neat package, by the way. It's really easy to use, but it actually has a lot of power in it too. And we're going to do all of that in today's lecture. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today will be our last lecture on response surface methodology, but we still have a little bit more to discuss. The first thing we have to discuss is, well, how do you actually use one of these methods in practice? Because what we're going to find is that it's actually better to not sample all of the data points that we need at once, but actually better to sample a few at the first run and then do a second run where we sample more depending on what we see in our first run. And we can use this to try to find the best places to optimize our process, whatever we're trying to optimize, the response variable, without collecting unnecessarily large amounts of data, right? Because that's, again, the whole kind of underlying, what's the word I'm looking for? Underlying theme of this course is that we don't want to collect a lot of data if we don't have to. And that's the first thing we're going to talk about today. After that, we're going to do an example with just some sample code in R so you can see how to deal with response surface methods yourself when you collect such data. And there's a really nice package in R that we'll look at, which can fit response surface models directly to the data. I mean, you could manually do it with linear models and the AOV function, but there's actually a great package that does it all for you, and we'll look at that today in the second half of today's lecture. So let's get into the first bit in the notes. All right, so today, again, the first thing we're going to talk about is the idea of searching and optimizing with response surfaces. Surfaces, excellent. Right, so this is the main idea, as I mentioned, is that we don't want to necessarily collect all the data at once. So we're going to consider, in this lecture, we will just consider the central composite design, CCD, for central composite design. Now, again, we should consider the response surface model that we wrote down before. So the model that we're trying to fit is a second order model. It's a quadratic surface. It's going to look something like y is equal to beta naught plus the sum of the linear terms, I from 1 to k of beta I xi, plus the interaction terms, which is I less than j, beta ij, xi, xj, plus the pure quadratics, which is going to be I from 1 to, is it k? Yeah, I was using k. K beta I xi squared, and then there's always some noise in there. And if we write this out in terms of matrices and vectors, we have a much cleaner look to it, which is going to just be x transpose b for the linear piece and x transpose big B x for the quadratic piece, the interactions and the pure quadratic terms, both of which are encapsulated in the matrix B, big B, that is. So what we're going to look at is what happens when we collect different data points, just like we did in the previous lecture, but how that relates to what parameters we can fit in our model and how we can turn the central composite design into a two-stage type design where we collect certain data points first, and then if they look good, we collect more data points second. So let's see, what are we doing? Well, first let's consider a center point. A center point has xi equal to 0 for all xi. Therefore, the responses look like y is equal to beta naught plus epsilon, and everything else is 0 here. So if we sample from the center point, we're basically getting a null model where we're just getting beta naught and some noise. Of course, if we're always assuming that there's some noise in our system, or else we're not doing stochastic optimization, and that noise is epsilon. Okay, we assume it has a normal distribution, but the point is that if I repeatedly sample from the center point, I'm going to get values that are around beta naught plus or minus some random noise, which will change with every observation. And then we'll say, let's say that we sampled the center point NC times. Is that what I want? NC, that's the notation I was using. And that's great because therefore, we'll do another therefore. Therefore, what I'm going to call y bar C, which is equal to the sum. I'll just use I again. I need a 1 over n. If we take the average, basically, of all the center points, we're going to get an unbiased estimator for beta naught. So y bar C, which is just going to be I from 1 to, I guess, n sub C of y I. I need notation for this. Maybe I'll just put a little c up in the exponent to indicate that we're sampling from the center point. Well, this is an unbiased estimator for beta naught, i.e. the expected value of y bar C is going to equal beta naught. Great, and I mean, if we assume epsilon is normal and the variance is fixed at sigma squared, we can even use just the properties of the normal distribution, or if it's not normal but close enough to normal, we can use the central limit theorem to get a sense of what the distribution of the sample mean should be. Okay, so that means we can use the center points to get a sense of what the constant, the intercept term beta naught, is going to be in our model. But there's actually more that we can look at. So if this is for the center point, well, let's look at the cube, or I'll call them the factorial points, just so we have a different letter than C. C for center, F for factorial points. And these have xi equal to plus or minus 1 for all I. Okay, so we talked about this last time. We have to choose a 2 to the k minus q factorial, fractional factorial design for fitting our response surface model, and we need to make sure it has a resolution that's called 3 star. That is, the resolution has to be at least 3, but we can't have any terms of order 4, of length 4, I should say, of length 4 in our defining contrast subgroup. Now, that's not directly relevant at the moment, because what we're going to do is we're going to get a new sample mean. So what I want to define y bar f, and this is going to be 1 over 2 to the k minus q. Remember, there are 2 to the k minus q cube points that we are sampling, depending on what we choose for q, and I guess whatever k is. So this is going to be the sum over, I guess we'll just say, I from 1 to 2 to the k minus q of y, I, and I'm going to say f. So we can also consider the average of all of the fractional factorial points in our design. Okay, so what is that? Well, if we, instead of writing it like this, well, I can bring up this to the this 2 to the k minus q, and the numerator becomes a 2 to the q minus k if I just multiply the exponent by -1. And now what I'm going to do is say sum over all. I'm just going to leave it kind of blank for a second because I'm going to say we want to sum over all of the points. And what we're summing, well, beta naught. We're summing I from, well, I can't use I now, but that's okay. I'll just say sum over all cube points because it's easier to write that than to come up with some tedious mathematical notation. Because inside what we're going to do is we're going to sum up, well, this is, what is yi? Well, it's just our equation here, I less than j, beta ij, xi, xj plus the sum I from 1 to k, beta I xi squared plus epsilon. So just the same thing again. Oh, and this is technically a curly bracket, just for consistency. All right, well, what happens when we sum over all of the cube points? Well, let's go term by term and figure it out. Well, if I sum up beta naught is constant. It doesn't care what cube point I'm at, it's always just beta naught. If I sum it up 2 to the k minus q times, then multiply by 2 to the q minus k, what I end up with is just a beta naught. Okay, so that's the first thing. Well, what happens to this next one? Well, for every value of I, I'm going to have xi could take on the value of plus or minus 1. Now, if we recall the balance condition, we know there will be exactly as many plus 1s as there are minus 1s. So if I sum over all of the cube points, I'm adding just as many plus 1s and minus 1s here, which means I'm going to get a 0 for that term. And the same holds true for the next one, because for any fixed value of j, I know that xi will have an equal number of plus or minus 1s, right? This is gets back to the idea of balanced and orthogonality between the columns. So what that means is that if I sum over all of the cube points, then if I average over them, but if I sum over them, I'm going to get another 0 here. So that same idea does not hold for the pure quadratic terms, because when I square xi, it doesn't matter if it's plus 1 or minus 1. When I square it, this last term is just going to be 1. And I'm going to add it up, well, 2 to the k minus q times, and then multiply by 2 to the q minus k. And what I'm left with is just a sum I from 1 to capital K of beta I. And then we're going to have the epsilons here, which I'm going to call epsilon bar, because technically we have 2 to the k minus q different epsilons, and I'm adding them all up and dividing by the total. So we have some like average epsilon term here, but most importantly, it's still mean 0. That's all I really care about for epsilon, even epsilon bar. Okay, so what happened here? Well, it tells me that if I extract all of the cubic point, or the cube points, I should say, the cube point or the factorial points from my central composite design, and I average them. So I average over all the points on the vertices of the cube. that I've included in my design. Well, what's the answer? The answer is going to be beta naught, the constant term, plus the sum of all the quadratic terms, plus some noise. So what does this mean? Well, this means, therefore, the expected value of this average, f, y bar f, is going to be beta naught plus the sum I from 1 to k beta I. So this is quite interesting because up above we have an unbiased estimator for just beta naught, but down here we have our unbiased estimator for beta naught plus some of the pure quadratic coefficients. And what we're going to do is we're going to use these 2 points, these two averages, that is, to try to determine if there's any quadratic behavior in our response surface. So the idea is that if all of the beta II, let me write down the intuition here. So the intuition is that if all beta II are equal to 0, i.e. no pure quadratic effects, then y bar c is going to be approximately equal to y bar f, I'll say up, which is approximately equal to beta naught up to, well, the noise epsilon. So we can use this to do a statistical test for significant quadratic effects, which allows us to collect fewer data points. Because if we go back, what did we not talk about? We didn't talk about the axial points yet. So far, we can imagine this as like, I went out, I collected the center points. I went out, I collected the cube or the factorial points, but I never collected the axial points. And what we can do is we can run a statistical test to say, should I collect those axial points or should I just forget about them and move on to a new place to search? So the idea here is that I'll say, therefore, we can test the hypotheses, which is going to be h naught, the sum of the beta II is equal to 0 versus the alternative hypothesis that the sum of the beta II is not 0, which in words is saying no, I guess, quadratic. And this is, I guess, yes, quadratic, or the presence of a quadratic effect in our surface. So roughly it's saying, does my surface look like some type of, that's a terrible plane. Let's try again. Does it look like some type of plane? Or does it look like some type of quadratic? If we can draw this, let's see. Well, that's not so bad, right? Maybe I can give it some contour lines in gray. Something like that. Cool. That's not so bad. And we can do some little gray lines like this here. So this is what we're doing. We're saying, does the surface look like a flat plane or does it look quadratic? Now, I guess technically we're just doing it could be an upward, could be, I guess, a parabola going up. It could be a parabolic surface, I guess I should say, going down, or it could be a saddle point. But this is roughly what we're doing is we're going to, so the idea Actually, well, yeah, we'll write down the method is collect, center, and cube points. Then, if there appears to be sort of non-zero quadratic effects, then collect the axial points. So I didn't actually write down the test statistic for this hypothesis test, but if we want to run this hypothesis test, we can basically just do a t-test. So comparing y bar c to y bar f under epsilon being normal, we'll say 0 sigma squared, is just a t-test, a two-sample t-test. Maybe I'll write that two-sample t-test. There are more than one t-tests out there. A two-sample t-test. All right, cool. So what's the statistic look like? Well, the test statistic is going to look like T naught, which is going to be the absolute difference between the two sample means. And we need to divide by some standard error, which is going to be S, the sample standard deviation, which I'll write down in a second. And we're going to have the inverse of the two sample sizes. So we have a 1 divided by 2 to the k minus q plus 1 divided by nc. Right, so this is the two-sample t-test for, I think, homogeneous variance. There's going to be different variants of the two-sample t-test for non-homogeneous variance, but there's a problem here, and that's that we have to assume homogeneous variance because we can only estimate the variance with the center points. So the center points are replicated, and since they're replicated, we're able to use them to estimate the sample standard deviation. So here, S is just the sample standard deviation. So if we write S squared as just 1 over NC minus 1, the sum over them is going to write center points of y, I guess I need I or something, minus y bar and c, or y bar c is the notation I was using, squared. So again, because we've replicated the center point, we can use that to compute the standard deviation, or the sample variance, which can then lead to the sample standard deviation. But critically is that we can't use the other points because we don't have replications at the cube point. We only have one for any of the vertices that are in our design, and we don't replicate those. So that's okay. That's perfectly fine, but it means that we have to be a little careful, and we have to assume that the variances are homogeneous, or else, because if you did a non-homogeneous t-test, you would have to estimate the variance of both of your samples, the center point and the factorial point, but we can't do that for the factorial points, so we're going to assume that we have homogeneous variance, which is kind of a standard assumption in much of this course. So whether it's true or not is up for debate, and there are other more robust methods that will try to account for such things. But at least for this course, we're going to assume that the variance is more or less the same at every point in our design space. All right, so I forgot to mention one thing. Let's give it a little bullet point here. Under H naught, that the sum of the beta II is equal to 0, we have that T naught, my test statistic up there, is going to have a T distribution with NC minus 1 degrees of freedom. And again, this is specifically because the NC minus 1 degrees of freedom is coming from the number of points used to estimate, well, sigma squared by S squared. So that's where the NC minus 1 is coming from, and why we want to replicate the center point at least twice so that we can get some estimate, a non-absurd estimate of the standard deviation. I mean, it may not be good, but it just has to be good enough. All right, so this is the roughly how we can test for quadratic behavior in our response surface without collecting the axial points. So yeah, let's talk about exactly how this would work in practice, and then we can go look at some R code, which is always fun. All right, so how can we use this in practice? Well, the idea is roughly this fold, kind of the, I'll call it the CCD method for central composite design. So step 1 is kind of pick a starting point, which would be some values for your factors, and code it to basically x1 through xk equal to 0, 0. So what we'd have to do is pick a starting point. Again, maybe it's like a common pressure, temperature, humidity, whatever setting for our design, whatever the inputs correspond to, right? That's what we're going to start with. We're going to just pick a reasonable value. It's like your oven, set it to 350 degrees Fahrenheit, say, and maybe pick a pressure for whatever. And then we encode that to be the origin, to be 0. And then we would also have to encode and I guess maybe we'll say 1A is also encode the points xi equal to plus or minus 1 and plus or minus alpha. So that way we have a sense of what we're doing. And then maybe we'll call it step 2 is collect some center points and some cube points. And then we can kind of go in 2 different directions. So we'll say if, I'm not very good at actually writing out like algorithms and pseudocode, so I'm just kind of making this up as I go along. If, let's say, we reject H naught, that the sum I from 1 to k of beta I is equal to 0, maybe we'll call this step 3. Yeah, we'll call this step 3 and then get rid of that bullet point. So if we were to reject this hypothesis, then collect the axial points. I'll say, and maybe more center points. That's always useful because if there's, again, if we're replicating, if we're collecting these data points at a later date, then if we want to be able to test for if other things have changed, then if we collect more center points, we can kind of say, did the old center points look like the new center points? That is beta not the same, or did something change, from day to day? Like I say all the time, if you ever go back and collect more data points, you should keep them in as you should include another factor in your model that says replication 1 and replication 2, or trial 1 and trial 2, because here we're not technically replicating the same data points, we're collecting new data points at different positions. But if we collect more center points, we can think of them as replications at a later time, and then we could use that to determine if anything else has changed in our design. So it's always good to do that. But yeah, anyway, then collect the axial points, maybe some more center points, and fit a second order model. And find the critical point, etc. So this is the first if. The second if is if we do not reject H naught, then what we said is we feel like it's more of a plane, then don't, well, maybe I'll just say, instead of collecting more data points, rather than saying don't collect more data points, I'll say rather than collecting more data points, then we just then use what we already have to fit a first order model, i.e. a plane. So a flat surface, a plane, or some hyperplane, I guess, if we're in k is greater than 2. Okay, so now that we've done that, we say then follow the direction of greatest increase, assuming that we're trying to maximize our output. If we're trying to minimize it, then we'd want to go in the direction of greatest decrease to find a new spot to sample more data points, a new origin, maybe I'll say, to be more precise than just saying spot. So a new origin being the point 0, 0, 0, 0 to sample new data points. Because the idea is that you might not initially find what you're looking for when you start your design. So what you might have to do is move to a new region in design space and then sample again, and then run the CCD, the central composite design, again. So roughly in a picture, what this would look like in 2 dimensions. So let's imagine we have our big 2-dimensional design space. All right, so what do we do? Well, first we start with some origin point. We'll call this is the origin, and then we're going to sample our factorial point, our cube points here. Something like this. So this would be the first part, step 1, is where maybe I called it step 2. Yeah, collect the center points and the cube points. Okay, so let's imagine that we did not reject the null hypothesis. So we think that there is no quadratic behavior here. That means that we just fit a plane here. So what we can do is we can fit a first order model and say that, the direction of greatest increase is that way. So we go that way, and there's no right or wrong answer how far to go in that direction. We'd have to go in some feasible amount. So if this is temperature and pressure, maybe we need to increase the temperature and increase the pressure. And we pick, following this vector, we could pick a new point that would be reasonable within the parameters of our design, right? Because there's usually some physical reality that I don't know what it is, because I'm just doing this hypothetically. But right, we would pick a new spot, and then what we would do is we'd collect our new points, and maybe we do this a second time and we again don't find any presence of quadratic behavior. And this time it says, oh, you know what you should do? You should look in this direction. So we follow it down here somewhere, and we pick a reasonable starting point for a new origin. And then we collect our cube points. And then maybe this time we actually do reject the null hypothesis, and it tells us, I think there's something quadratic going on here. So then what we do, we say, good, in that case, I'm going to collect my axial points in blue here. And then now that I've collected my axial points, I can fit a second order model. And the second order model is going to, well, if we look at it in terms of like contour lines, it's going to look like a bunch of concentric circles, which I'll try to draw here, something like this. This could be our second order model. And then we identify our critical point here in the center of it. So, right, let me just write this in. This would be like first order, move to a new location, first order, move again. And then we would do our second order. And then we would find our critical point. So this is roughly what you could do. And the point is that we're saving those 4 axial points whenever we don't need to collect them. So when we started this design, we collected 5 points, or maybe we replicated the center point twice. So let's say we collected 6 points with 2 center points and 4 cube points. And then instead of collecting those other 4 axial points, we move to a new location. Then we replicate the design again, but at a new location. Then we move to another location. We replicate it again. If we find some significant quadratic effect there, then it says, we should go collect those axial points so that we can actually fit all of the parameters in our model. So that's what we do. We collect all the blue points. We fit our second order surface. Hopefully, it's a parabola that's parabolic surface that's facing in the right direction and not either a saddle point or going in the wrong direction. And then what we can do is we can identify the critical point there. And then we say, that red star, that's exactly the temperature and pressure settings we need for our hypothetical machine to give us the most output that we want, right? So this is like an idea roughly of what you might expect if you're running a response surface. Now, there's always a lot of physical restraints. How many points can you actually sample? How far do you move in each of these directions? There's no right or wrong answer. It really comes down to the specifics of the setting that you're running your experiment in, which can affect a lot of things. I mean, sometimes you have design spaces with hard boundaries. So I just drew my little blue box here, hypothetically, to say, we're going to search in this region. But there could be a hard boundary where it's like, we can't turn up the temperature past this amount. It only goes so high, right? Or maybe the pressure can only go so low or whatever in our machine before it just breaks down, or there's some hard limits there. So there is a chance that you won't be able to search forever in any direction. You might just get stuck at a boundary. But this is, again, just an abstract picture of how you might run a response surface in practice. But what's even better than talking about an abstract picture is actually doing it in practice. So that's what we're going to do now. We're going to jump into RStudio, and we're going to look at this chemical reaction data set that you can find in the RSM library. So just to write it down so it's written in my notes, in R, there is the RSM package on CRAN, which is, or CRAM, CRAN with an N, which is the response surface methodology package. And it has a really nice function for both coding data and fitting response surfaces to that data. So let's go see how to use that function. And now we're back for the second half of our lecture today. And what we'll be looking at is the RSM package in R, or in RStudio, I guess, to be precise. So what we have here is the package that's, well, dedicated to response surface analysis. And it's a fairly nicely done one that has many different functions and things that you can use here, as well as some interesting data sets to look at, which we'll be definitely doing in this course. And fun fact, it looks like it was coded. The author and maintainer is Russell Length, who I'm 99% sure is the same Length who came up with Length's method that we discussed earlier in this course. So thank you for coding a very awesome package. Anyway, what we have here, the main function we'll be looking at is RSM, which is RSM package. So the RSM function in the RSM package, right, will fit a response surface regression. So it works really the exact same way that you would see the LM function working if you were to fit a linear model. In this case, we give it a formula, we give it a data, and it tells us what our response surface is. The nice thing is that instead of just using the linear model, we can use these special functions, FO, SO, TWI, and PQ. And these are going to correspond to the pieces of interest for our response surface. So remember, for a linear model, LM, you can just throw in whatever terms you want. But for the response surface, we have some very specific terms that we are interested in. We have the FO, the first order terms, or the linear terms. We have SO, the second order. The second order can be broken into two pieces, which are the two-way interactions, TWI, and PQ being pure quadratic. So each of these can be included or excluded when fitting a response surface in order to, well, understand the data and the how the model fits the data. All right, so the first thing we need to do is load it in. I've already loaded this in. And then we're going to look at the chemical react data set, which we're going to code. So notice here, and this is as I mentioned in the first response surface lecture, that we have to consider coding our data before we put it into a response surface. So if we were to, we have this nice function here, which will code the data for us. So the data itself, chem react, looks like this. We have time inputs, temperature inputs, a block, which is going to be the first run and the second run of the experiment, and then we have a yield. Some sort of, I guess, the amount of chemical produced. I believe this R documentation is somewhat opaque. Yeah, all it says is we have a central composite design, which is good because that's the main thing we've been talking about in these lectures. We have two factors and two blocks. And yeah, the design variables are in actual, not coded form. And yeah, I don't think there's anything else. Yeah, the yield of the chemical process. So it's a little opaque. I guess we could go look up this textbook if we wanted to learn specifically what this data set is doing. But roughly, we set a time and we set a temperature and we get out a yield and we want to maximize the yield. So, well, first we have to code it. And that's what this coded data function does here. What I've done is I followed, well, the example that they had somewhere in here. I have to remember where it was, but where we basically turn time into x1 and we turn temperature into x2. And we do that by first, for time, subtracting 85. So 85 becomes 0, becomes the origin, and then we divide by 5 to scale everything. So same with temperature, we subtract 175. Notice that it wrapped around here. Let me change that slightly so maybe it's less. There we go. So we subtract 175 and then we divide by 5. And what we get is the data frame CR. So CR is going to give us the time, the temperature, and the yield, but it's going to say that the data are stored in a coded form using these formula. And the nice thing is we can take this coded data, shove it into the RSM function, and it'll just know what to do, which is awesome. We don't have to worry about all of the switching things to ones and minus ones and then switching back again and all of that headache. I guess before we do go forward, though, what we can do is we can look at time, or I should say chem react $time, or temp doesn't really matter, whichever one. My point is I just want to say that if I actually apply this formula to it, if I subtract 175 and divide by 5, what I get is I get -1 + 1 -1 + 1. So these first 4 points are going to correspond to our factorial or our cube points. Then we get zeros for the next 6. So we have a first run in block 1 of 3 center points. Then we have a second run of 3 center points in block 2. And then the final 4 points in block 2 are the axial points. Notice that here, their value is either going to be 0 or it's going to be the square root of 2. So this is a spherical design because we're setting alpha. Remember, that's the value at the axial point. We're setting it equal to the square root of 2, which is, well, the number of factors we have. We only have 2 inputs to our model. So this is a, I guess, spherical response, spherical central composite design. Yes. All right, so this is what the data looks like. Let's actually, you know what, before we get into this, why don't we look a little bit closer at the data just to see what happens. So if I plot chem react with time, and then I plot chem react with yield, I get a plot that looks like this. Okay, so it's not quite clear what's going on here. We see that for a low time, the yield is kind of low at this one data point, but then, yeah, it's not really clear, right? If I tried to just do classic linear regression, time versus chemical reaction, it's not really clear what's happening here. We have some points that are up, some points that are down, and all over the place. If we look at temperature, we see a similar thing. We have this peculiar spacing out of our points. Now, again, our data is actually coming in, our inputs here, right, are kind of discrete factor levels. So even though it is a continuous variable, underneath it is good to remember that. All right, so forget about the plot. Why don't we try to fit a first order model and see what happens? So what I want to do is I want to treat this data like it was collected in 2 separate batches, much like we discussed in the written portion of today's lecture earlier. So the first thing I'm going to do is fit a first order model using the FO function here. So notice I say yield is a function of x1 and x2, but only the first order terms. And I give it a subset of 1 through 7. So I'm only taking the first 7 data points, which are, again, the 4 factorial points, the cube points, that is, and 3 center points. So I fit the model, and I look at the summary. And what does the summary tell me? Well, it tells me a lot, actually. It has the usual linear model output, which gives me an intercept. So that's the beta naught, right? That's the global mean or mean yield, which is about 82.8. Okay, great. We also get estimates for x1 and x2, which correspond to the slopes that is beta 1 and beta 2 in the equations that we looked at earlier. Now, the intercept, yeah, it's significantly different than 0, but that's not too surprising, right? Because our data is all very much greater than 0. What's more of note is that neither x1 nor x2 is significant in the sense that the value of the slope is not much bigger than the standard error. In this case, it's smaller, so our t-values are not significant, meaning that at least from a main effects or a linear perspective, we don't see any change in the yield based on either the first or in either of the first order directions, or the main effects, you could say. So it seems like neither temperature nor time is affecting the yield, at least linearly. But there could be a quadratic effect. So let's look a little bit closer at the output. We get the usual linear model output about adjusted r squareds and r squareds, which at least in this case is really low. We get our p-value for our f-test. That's not significant. Then we go down to this interesting analysis of variance table. So there's two things. There's kind of like, well, a couple things to look at. First, there's the first order terms, which are 2 degrees of freedom, because I'm including the main effect of time and the main effect of temperature wrapped up together in this 2 degrees of freedom. And they have an f-test, which is the same f-test that's being performed up here. It's just repeated in the ANOVA table. And it's being compared to the residuals. Now, here, there's a couple more degrees of freedom here, but you have to look at the first 2 rows of this table. Just go down to the residuals. We had 7 data points to look at, right, for the first run of this experiment. Now, what we did was we used 2 of them to estimate the first order model. There's always one that's lost to the intercept term, or the global average. That's up here at the top, just falling off the top of the screen. And that leaves 7 minus 3 or 4 degrees of freedom left for our residuals. So we get our residuals as usual and can use those to check the f-test. There's another interesting thing that goes on here, which is they actually split the residuals in half into something called lack of fit and pure air. And here we're getting something that looks kind of significant. So that's kind of interesting. We didn't really discuss this, but this gets into the idea of how well the linear model kind of fits the data. Now, this gets back to the idea of not just that, but the idea that there could be a quadratic surface here in disguise, and we want to test for that. So we can actually go a little bit further and specifically test for that. But before we do that, I wanted to finish by looking at, remember, we're fitting a linear, I guess a plane. It's 2 dimensions, so it's like one plane, a 2-dimensional plane to our data set, and R will tell you what the direction of the steepest ascent is. So if we had significant first order terms and we had insignificant testing for our quadratic, then it would tell us that this is the best direction to go in to increase the yield, which is start at the origin, that is the 0, 0 point, which corresponds to, I think, a time of 85 and a temperature of 175, and go in this direction. And this is, I believe, coded, but then they go to the original units, which says for every 4 units of time, we should increase temperature by about 3 units. Now, the first order model does not really fit the data well, so we don't want to actually do this, but that's what it would, if you did get a significant fit, it would tell you that this is the direction you would go in order to best increase the yield for your whatever process is producing your data. So now what I want to do, though, is say, let's try to fit a model that includes the first order terms and the pure quadratic terms. So notice in this code up here, I now have FO and I have PQ. So I'm ignoring all of the interaction terms, and I'm only looking at the first 7 data points. So if you recall from the lecture, what I said was we need the axial points to estimate the pure quadratics. So right away, this shouldn't work, right? Well, it's going to give me something that's still interesting. First, it's going to give me a warning that says some of these coefficients are aliased. So I can't use response surface method, so I'm just going to treat it as a linear model. Okay, so it gives me the usual linear model output where it estimates my parameters, but now things have changed a bit. Well, first of all, we seem to have now, for some reason, significant first order terms, so that changed. But we also get one pure quadratic term and one NA term. So what happened here? Well, if you recall from the lecture, what we just wrote down was that when you only have the center points and the cube points, you can still get an estimate of the summation of all the pure quadratics. That is the sum of beta I from 1 to k. So in this case, minus 2.19 is not the coefficient for x1 squared. It's not the coefficient for x2 squared. It's the summation of those two coefficients into one. So they've been aliased, or I guess they use the term aliased here, because they've overlapped each other. All of the idea is that all of the pure quadratic terms, in this case, there's only two of them, but even if we had more in our model, they're all aliased together. So when we estimate one, we're kind of estimating the sum of all of them. So what we can do is we can use this to determine if there is some significance in our in the pure quadratic term. All right, so what ends up happening is that we have all of the pure quadratic effects effectively wrapped up into one estimate. And at least here, what we find is we get a significant p-value. So that seems to be indicating that there is some significant summation of all the quadratic effects. That doesn't mean that any individual quadratic effect is significant, but it means that somehow in aggregate, there seems to be some quadratic behavior going on here in our data. Now, we can actually do this manually. So if you recall what we just talked about in the lecture, hopefully you recall what we talked about, because for me, it's actually a couple hours later. For you, it should be kind of instantaneous that we switch from written notes to R code. I went and got some dinner. So anyway, right. So what we have here is that we can compute the mean YF, and YF is the mean of the factorial points like we just wrote in the lecture. We also have YC, which is the mean of the center points. And if we subtract the mean of the factorial point from the mean of the center points, what should we get? I think we just saw it there. It's minus 2.19166. Oh, that looks exactly like, well, this number. So you can see exactly what's going on here. When we look at the difference between the mean of the factorial points and the mean of the center points, we get an estimate of the pure quadratic effect, all effects all aliased into one. So I think that's kind of neat. I like that. Furthermore, did I put that in here or did I not? Oh, no, I don't think I actually did that. Okay, well, we'll do it manually. What we can do, right, is we can actually compute the test statistic that we talked about in class. So if I take the absolute value of these two things and I divide by an estimate of the standard error, in this case, I want the standard deviation computed on just the center points. Remember, the other points I can't use because their mean values might change and I don't have replications at those points. And I multiply this by the square root of the sum of the reciprocals of the sample size. In this case, I have 3 center points and I have 4 factorial or cube points. That gets me a test statistic of 13.78. And if we use the the t distribution with 13.78, we'll say 5, 13.785 that is, And then we tell it that we want how many degrees of freedom. Well, we needed NC, the number of center points, minus 1, which would be 2. 3 minus 1 is 2. And I also need to tell it to do the upper tail, so I say the lower tail is false. And we get a p-value of 0.0026. If we want to do this as a two-sided test, we can double the p-value, and we still get something that looks like 0.005. So what this is telling me is that we have pretty significant evidence that there's some quadratic effect here. This is similar to testing this thing, but this thing is tested slightly differently because here it's tested as a t-statistic with 1 degree of freedom, whereas down here we're testing it as a t-statistic with 2 degrees of freedom. Also, I believe the standard error should change slightly. Notice that here the t-test value, the t-value is 12.8, whereas down here I had a 13.7. So it is slightly different what they're doing up here than what they're doing down here. Here they're treating it like a linear model. Down here we have more knowledge, right? The LM function just says this is a coefficient in a linear model, do a t-test. What we're saying is, but we actually have more of like a 2-sample test going on down here, and that's how we're gonna treat this. Either way, we get significant p-values, so there's no ambiguity there between, say, this line and this line. Right, so if we have evidence that there is a quadratic effect, then that means what we need to do is, well, collect the other half of our data set, that is, sample some more center points, sample the axial points, and fit a second order model. All right, so now we're going to fit a second order response surface model to our data, and this is really easy to do. In this case, we just tell it that the yield is a function of x1 and x2 put inside this second order function. And I love the simplicity of writing the formula for this R function, because if you actually had to write out all the terms, it would be really annoying. There'd be x1, x2, and the cross terms and the quadratics that you have to code in separately. In this case, just type in SO and you get everything you need. So we fit that, and we look at a summary, and now we get lots of different stuff. So this is kind of neat. First of all, we get our intercept. Then we get a whole bunch of terms. Interestingly enough, none of them are actually significant. So we don't have any significant p-values here, but we do have a quadratic surface. We get, that's interesting. I didn't know you could have a negative adjusted r squared. I'm going to have to look at the formula for that. I'm surprised that's a thing, but that's okay. We still actually don't get quite a good fit. But you can at least see what's going on here with our new updated analysis of variance table. So in this case, we have 2 degrees of freedom for the first orders. That's x1 and x2. We have a single interaction term, x1 times x2, and that gets its own entry. Then we have 2 degrees of freedom for the pure quadratics because, again, we have an x1 squared and an x2 squared in our model. We get our residuals here. If we add them all up, we should get the right amount of data points, right? Points of data, because I think what we had was we had 4 cube plus 4 axial is 8 plus 6 center point replications, which gets us 14. And then if we add all of these up, hopefully we get, well, 13, I guess, yeah, which is 8 plus 5, which is going to give me 13, and then with 1 extra for the intercept term. Now we still have this split into lack of fit and pure error. Here the lack of fit is no longer has a small p-value, so we have in some sense a better fit with respect to that. Maybe if we have time, we'll talk about some of more details of this later. Anyway, R will also calculate, the R function, RSM, will calculate a stationary point for your response surface. In this case, in coded variables, note, it says that the optimum, the stationary point, again, could either be a min, a max, or a saddle point. So you have to be careful. We don't know what it is yet. We just know that there is a stationary point because we fit a second order model, and that stationary point is at 0.37 and 0.33. And if we go back to our uncoded time and temperature, we get 86.8 for time and 176.67 for temperature. Now, what's really important is the bottom. The bottom here is going to tell us what the Eigen Analysis, and this is the eigenvalue decomposition of that matrix B that we talked about. That is going to tell us what the local behavior of around our stationary point is. Both of the eigenvalues are negative, and that's good because that means that we have a local maximum. Remember, if both eigenvalues are negative, we have a max. If both are positive, we have a min. If we have one of each, we'd have a saddle point. And we also get the eigenvectors. This can be useful, especially if you have things like saddle points or maybe a local minimum so that you can determine what the direction of steepest increase is. All right, so again, we don't get a lot of significant test statistics, but you can at least see how we fit the a response surface to this data and what it would look like. And we have all our coefficients up here. So notice that both quadratic terms pure quadratics have negatives, which is good. That means we're at a maximum. And we have an interaction term, which is kind of small here. I guess they're all small with respect to the standard error. Anyway, I can plot this, but actually, yeah, why don't we plot this first, just because I think looking at the picture is really cool, and then we'll look at the model matrix and conclude. So I took some time to write all of this out because it looks really neat when we do it. So what we do is we use contour and model to the quadratic model, and this to basically fit to draw out the contours of the quadratic surface. So a contour line, right, just in case so we all know what we're talking about here, is a line where the quadratic surface takes a constant value. So you can think of it like one of those topographical maps, I think is the word I want, where you see lines indicating hills and valleys on a map, right, for the geography of a region. Here, what we're basically saying is we have a minimum, and as we start to go up, by different values. So here, if we stare really closely, it looks like we've got 81.5, and then 81, and then, actually, I'm not quite sure. Oh, that's right, of course, we have a maximum. Yeah, we have a maximum, of course we do. So as we move through these lines, we're actually going down to like 76 yield and 77 yield down here. Anyway, let's plot some points. So that red dot is our center point. That's the center of our response surface design. Our factorial points are there, those red hollow circles in the four corners making a square. The axial points are going to be here, the red X's. So you can see the axial points along the axes and the factorial or cube points making the square here with our red solid center point in the center. Now we can use polygon here to draw some lines, which is great because now we have our square, and we can even draw in the axes. So you can get a sense of what the central composite design looks like in this case. Oh yes, I also drew some arrows. That's the direction of steepest, which one is that? Steepest increase, starting from the center point. And, oh, this was for, I think, the first order model. Yeah, for the first order model, so it doesn't coincide with the contour plot, but if we just plotted the first order model, what we would find is we should go in the direction of the green arrow to increase our output. Now, the stationary point is right in the center of that circle in blue, and that's going to be the main thing that we want. Now, granted, this model did not have a very significant or strong fit, so whether there's not really much of a statistically significant difference from the center point to this local maximum, but still, it gives you an idea of how you would do a response surface. Lastly, I thought it's interesting to look at the model matrices. So as I say here, right, we can see why we need these extra terms. So this gets back to what I did in class. If we look at the model matrix or the design matrix for the first order model, we just have standard intercept column. We have our -1s and +1s for the cube points, and then we have our center points down here replicated 3 times. If we try to fit the pure quadratic terms, let me get myself a little bit more room here. Maybe I can get them all onto one page. Yes. Then what happens? Well, the columns for the 2 pure quadratic terms are identical. They're all 1s followed by all 0s. If the 2 columns in your design matrix are the same, those terms are, well, I would say, I guess, confounded or aliased, depending on what kind of terminology you want to use. I guess in this case, we could call it aliased because there are 2 different effects that coincide, whereas confounded is more like if you include some other blocking factor that coincides with one of your other experimental factors, then it gets confounded. Though the 2 concepts are extremely similar in practice. And I think this is a good visual explanation of why we need the axial points. Because now with the axial points, we have differences in our pure quadratic. We have 2, 2, 0, 0, and then 0, 0, 2, 2. And what that means is that our quadratic columns are no longer identical to each other, and that means we can estimate coefficients for each of the pure quadratic terms. All right. So that is more or less what I wanted to do with response surfaces. Now, there are other data sets in here, I believe, that we will look at. We had ChemReact, which we looked at today, but I'm pretty sure there's another one. Yes, Heli, which is a perhaps more interesting data set. This is one that you get to look at in your final assignment for this class, which is kind of a neat one. This one has 4 different dimensions for making, I think, a helicopter or something. I think a paper helicopter. But because we have 4 different dimensions, it makes it a lot more interesting. Luckily, this data set is already coded, so you don't have to worry about coding it yourself. And yeah, so that is, again, more or less everything I wanted to talk about response surfaces. There's still a lot that you can read up on response surfaces and how they're used in practice, because they are quite a really powerful tool for optimizing some process that you're working with, some industrial process or even something else. So hopefully you found this interesting, and we'll be moving in now to the final section of our notes, of my notes, which is basically all the other strange designs that I didn't have a chance to cover earlier in the course. So we still have a couple lectures left to go, which is great because it means we can look at a bunch of different strange designs. They can get a little messy. So stick with me, and I will see you in the next lecture.